Hello everyone, this is Dr. Andrew Chrysler teaching EE 4418 at Idaho State University. In this lecture we'll be covering Chapter 4.6 on bandwidth analysis of angle modulations. You can follow along in the 5th edition of Modern Digital and Analog Communication Systems on pages 225 through 233. So let's recall our original motivation for investigating angle modulation. Remember, we were thinking about the double-side band suppressed carrier signal and the fact that it had a bandwidth of 2B. And we thought maybe if we apply angle modulation, we can actually reduce that bandwidth, because if we have less bandwidth, this will cost less money. So the idea was, if we applied a phase modulation where we had the angle of the cosine being modulated with this term kpmt, if we made the term kp very small, perhaps we could make the bandwidth of the modulated signal phi pmt very small. So maybe what the original idea was that we could transmit some message with no bandwidth. So what we want to see now is this really possible? What actually happens? So in the previous chapter, 4.5, we looked at some things like instantaneous frequency and what it really meant to come up with a modulated PM or FM signal. So to start with, if we remember, we had the AM modulated signal, which had some amplitude A plus the message multiplied by a cosine at carrier frequency omega c. And then we have these two angle modulated signals, PM and FM. The PM one modulates the angle, whereas the FM one, we have this modulation of the instantaneous frequency. And the angle, omega ct, is linear for AM signals, so we can use Fourier transform to analyze the bandwidth directly. But for FM and PM, the angle is nonlinear, so we can't use the Fourier transform directly. So we're going to need to come up with another way to find the bandwidth of PM and FM signals. So we can't use the Fourier transform, so let's apply some mathematical expressions to see if we can find another way to analyze the bandwidth. Okay, so let's start by looking at the FM signal. And we'll say that the modulated FM signal is phi FM. So as we looked at in the previous chapter, phi FM is some amplitude of a signal that's fixed multiplied by a cosine, and that cosine wave has a carrier frequency omega c, and that is multiplied by time. And then we have this other part that's the modulation, and that's some kf multiplied by this integral of the message that we want to send. So we want to send this message. So let's see if we can simplify this expression. So we'll define this integral by calling it at, some function at. And at is the integral from minus infinity to t of the message. Or if your message starts at time 0, you could also just write at as going from 0 to time. So by doing this, we can rewrite the modulated signal of phi FM. We can rewrite it without that integral and instead use this function at. Now, if we have this FM signal written like this, we can see from Euler's formula, if you remember, that we can write some exponential, some complex exponential, as a combination of cosine and an imaginary sign. So the real part of that exponential e to the jx is cosine x. Or mathematically, we could say that the real part of e to the jx is equal to cosine of x. Now, our modulated signal, phi FM, contains a cosine. So if we look at this part, let's take this cosine and say that we could rewrite it as the real part of some complex exponential of e to the j omega ct plus kf times that function at, and that's that integral of our message. And you could split up that exponential like this, so that we have e to the j omega ct multiplied by e to the j kf at. So now we have this phi FM, so the modulated FM signal, we can write as the real part of this series of complex exponentials. So if we have a modulated FM signal that looks like this, and we're taking the real part of this, let's see if we can simplify this a little bit further. Because remember, what we're trying to do is we're trying to find the bandwidth of this modulated signal FM. So we need to simplify this in a way so that we can find the bandwidth. So let's look at this part. Okay, so this is a complex signal. So let's rewrite this as this phi FM hat. So just to remember, this phi FM hat with the hat saying that this is the complex signal. So it contains all the complex parts. So later we're going to go back and look at just phi FM, but for now we're going to look at the total, which has some real parts and some imaginary parts. So we'll study this complex signal first. So again, just to remember, we're going to go back later, and the modulated signal contains only the real parts, but for now we're going to study the complex signal. Okay, so this complex signal is a e to the j omega ct times e to the j kf at. Now let's look at this last term, e to the j kf times at, and that's the term that contains that integral, and that part is nonlinear. So this is the integral of the message. So let's use a trick that we looked at before, which is power series expansion. So we know that a exponential, e to the x, could be written as a power series expansion that looks like this. So let's use this and apply this power series expansion to that e to the j kf at. Okay, so if we do that, we can rewrite e to the j kf at as a power series expansion, and it's going to look like this. And if we simplify this, you can see that some of those terms contain some things like j squared or j cubed, and we can rewrite those j squared parts as minus 1. So from this power series expansion, we can rewrite this phi FM hat like this. So a times e to the j omega ct multiplied by a power series expansion of the term that contains that function at. Okay, so now we can also see that if we take this e to the j omega ct, we could apply Euler's formula to this also. If we do that, we can substitute in like this, and then if we distribute this, we're going to have a whole bunch of terms. Some of them are real, some of them are imaginary. And then if we multiply all of this through, we're going to get something that looks like this. And of course, this power series expansion would contain an infinite number of terms, but I've just written a few here. If we simplify again, so that anytime we see j squared, that's equal to minus 1, we're going to simplify it a little bit more to this. And again, we just showing a few terms here. But don't forget our goal. We want to find this FM modulated signal, which is the real part. So looking here, right, this phi FM hat, this contains real and imaginary parts, but we want the expression that contains just the real parts. So where are the real parts in this? Well, let's take a look. This one's real, this one's real, this one's real, and this one's real. So every other term, it kind of goes back and forth between whether the cosine part is real or the sine part that is real. So if we want to find this phi FM, so the modulated FM signal, it's just the real part of that phi FM hat. And so now we have an expression for the FM modulated signal that contains the real parts only after applying this power series expansion. All right, so this is starting to look a little bit better, right? Because now we can see, look, if we have a whole bunch of terms, and in those terms, there are a bunch of cosine or sine waves that contain the argument, which is omega c, which is the carrier signal, and then in front, the amplitude of these is now that nonlinear part. So we were able to move, by applying this power series expansion, we were able to move that nonlinear at from being inside the argument of sine or cosine to being in front of it. So we were able to move it to being that amplitude. All right, so we're getting a little bit closer, and now we can see that our expression for the FM modulated signal is pretty similar to the amplitude modulated signal. right? So originally we had this amplitude modulated signal that we studied before that looked like this. And that amplitude modulated signal, our carrier frequency times t, that's the argument of the cosine, whereas our message is modulating the amplitude. So we were able to rewrite the frequency modulated signal so that it looks kind of like this, where we have at, something containing the message that's modulating the amplitude. All right, so we still want to find the bandwidth of this frequency modulated signal. So let's think about what the bandwidth of the AM modulated signal is. So the message is going to have a bandwidth, and that bandwidth is going to look like this. So the signal, we could say, has a bandwidth of B. So what's going to be the bandwidth of AT? So what's the bandwidth of that integral? Well, if the message has a bandwidth of B, then A of t is also going to have a bandwidth of B. So why would we be able to say that? Well, integration is a linear operation in the frequency domain. So remember this table, 3.2 on page 123, has some properties of Fourier transforms. Look at the bottom one, time integration. Well, we can see if we perform integration in the time domain, then that's going to give us some frequency domain property, GF, and that GF is just being divided by J 2 pi f. So because our frequency domain signal is just being divided by J 2 pi f, it's going to have the same bandwidth as GF. So that means that A and T are going to have the same bandwidth because that integration is going to be a linear operation in the frequency domain. All right, so if A of t and M of t have the same bandwidth, what about the bandwidth of a squared t and a cubed t, and so on, because this is going to have an infinite number of terms? And what about even the bandwidth of a very high order term, a to the n? Well, a to the t has a bandwidth of b, then a squared, that's going to be the convolution of a of f with a of f, and that's going to double the bandwidth. And if you have a cubed, that's going to be the convolution of a of f with a of f, and then the convolution of that with a of f. So that's going to have a bandwidth of 3b, and so on and so on. So if you have a to the n, that's going to have a bandwidth of n times b. So each term of the frequency modulated signal has more bandwidth than the previous one. So as n gets bigger and bigger, all the way up to infinity, which is the amount of terms that the power series expansion has, we can see that that final term is actually going to have an infinite amount of bandwidth. So this one has 0 bandwidth, that one has bandwidth b, this one has bandwidth 2b, this one has bandwidth 3b, and if you just keep going and going as far out as that power series expansion goes, you're going to have a bandwidth of nb. Well, that's not good, right? Because bandwidth, we said, was expensive. So this means that the frequency modulated signal actually requires infinite bandwidth. Well, that's the exact opposite of what we originally wanted, right? Well, let's even think about this some more. So eventually we're going to reach that very high order term with coefficient k to the n times a to the n of t over n factorial. But the good thing is that if n is a very big number, that's actually going to basically turn that coefficient into being equal to 0, which means that most of the signal power of our frequency modulated signal is actually going to be in the first terms, the early terms of this power series expansion, because that's where most of the signal power is going to be constrained, where the terms of n are actually pretty small. All right, well, that was a little bit of a long one, so I'll see you in the next video.